this morning session. We have two speakers. The first speaker is Professor Gerrit Bauer, and he's a key theoretician on spintronic in the past 10 years. So he's working mainly in Tohoku University. Today he's going to tell us about the spintronic and spin characteristics with the magnetic instrument. Let's welcome Professor Bauer.
Okay. Thank you very much, Professor Guo. I would like to thank the organizers and especially Professor Guo for the great organization of the whole conference and the generous support. It's a difficult task to speak after Professor Saito, and there will be some overlap, but I hope that some repetition will not do any harm. These are the topics I have for you. I will have some basic introduction in the beginning, and then I would like to discuss a couple of recent results. Let me also give a piece of history. Here's a picture of Thomas Seebeck, who started the fields of thermoelectrics. Here you see the basic experimental apparatus, which consisted of two different metals which are soldered together at two places, and if you heat one side, the magnetic needle here started to move. So this is the discovery of the Spin-Seebeck effect of thermally excited charge currents. The thermoelectrics was put on a firm theoretical footing by Lars Unzager. Here you see the memorial plaquette of the Trondheim University, and there is a mathematical equation, Lij equals Lji, for which he got the Nobel Prize in Chemistry. The Unzager theorem is a fundamental theorem on non-equilibrium thermodynamics. Consider a system which is described by a number of thermodynamic variables like mass, charge, and so forth. We can disturb an equilibrium system by forces like electric fields or temperature gradients, which generate currents, which can be charge currents or heat currents. In linear response, these two are, for weak forces, these two are related by linear response. The coefficients here are constants, but we see that there are constants between different forces and currents, and thermoelectricity is one example of that. So there is a response matrix. If you normalize the currents and the forces such that the sum of their products equals the dissipation, the entropy generation rate, then Unzager proved that this response matrix must be symmetric. The reason for the symmetry is time reversal symmetry of quantum mechanics in time reversal irreducible, of course, it's not time reversal thermodynamics. Of course, in the systems when we have magnetic fields or magnets, we know that time reversal symmetry is broken. Then we have to be a little bit more careful in order to derive the symmetry. We have to reverse magnetizations and magnetic fields here, and have to take into account phase factors. But in principle, it is the same. Now, how does it work in thermoelectrics? Let us consider an electric wire here, which connects the two poles of a battery. This battery, when it is charged, then there will be a voltage difference delta V, and we can also assume that there is a temperature difference delta T. Clearly, this is a non-equilibrium situation, and currents will flow, the charge current and the heat current. So we can write then the relation between the forces, delta V and delta T, properly normalized like that, and the charge current and the heat current is the response. Now, according to Unzager, we now know that this matrix must be symmetric, the non-diagonal elements must be equal. This looks unfamiliar, but we can transform it into more familiar historical coefficients, and this relation is here. So we see, for example, that if we have a delta T, the Seebeck coefficient S will describe the thermoelectric voltage which is generated. And the same holds here for the Peltier coefficient. Now this equation is just a linear transformation from this equation, and we know from the Unsager reciprocity that the Peltier coefficient equals the Seebeck coefficient times temperature. So if we know one effect, we automatically get the other one, which saves a lot of time. These type of relations exist in many areas of physics and chemistry, and that's why Unsager got the Nobel Prize for it. And it's also a very useful principle in spintrons. Next, I would like to discuss the generalization of conventional thermoelectrics to to magnetic systems, to spin-dependent phenomena. Let's first recall the basic experiment, the basic concept in magnetoelectronics, which is indicated here in the form of a bilayer of a metallic ferromagnet and a normal metal. We know that in a ferromagnetic net we have two types of carriers, the majority spin and the minority spin, which have different electric resistances. In a normal metal, the electric resistances are the same. So this bilayer can be written of, as far as transport is concerned, by an equivalent circuit like indicated here. So if we close this switch here, the electrons will flow, take the part of the lowest resistance, which is the upper arm. So more of one spin will be now injected into the normal metal than in the other one. We are then generating a non-equilibrium magnetization in the normal metal. This non-magnetization has a finite lifetime, and it exists over a finite length scale, which are indicated here. Now this spin flip diffusion length, this length scale, this can be microns or longer in favorable cases. Now we can parameterize the spin accumulation, this magnetization in the normal metal, by a non-equilibrium difference in the chemical potential of these both carriers. Now it's easy to generalize now the spin injection experiment by not applying a voltage difference, but a temperature difference over this bilayer. I think we should now know what is happening, because not only the electric conductances, resistances, but also the thermoelectric coefficients for spin up and spin down channels will be different. That means that driving heat current through the system, we of course generate this charge current, this normal Seebeck current, but it will be spin dependent. And the balance, the difference between the thermoelectric coefficients for up and down spin will generate the spin current and spin accumulation also in the normal metal. So basically the same thing happens like in the charge-based spin accumulation injection. So we can call this a thermal spin injection. Now several experiments have, first of all, theoretically we can again use Unsager's principle, but we have now to add an additional force, and we have to add an additional current. So in this case, this would be the spin accumulations, spin chemical potentials or voltages for up and down spin, and we have an upspin current, downspin current. Now we can transform this a little bit. Now here driving forces are the charge voltage, the spin accumulation, and the delta T. And these currents are the charge current, the spin current, and the heat current. The parameters here are P, which is the difference, or the polarization of the conductance of the ferromagnet plus interface, while P prime is the polarization of the derivative of the conductance. Now the interesting thing is that this P must be smaller than 1, obviously, but P prime is not bounded. Now if you look at such a matrix, then each of these elements corresponds to a different physical effect. P prime ST coefficient here says that governs the process that delta T, the temperature difference, generates a spin current. We discussed this. But there's another one, the same magnitude, and we do not have to do any calculations for that, says that if we have a spin accumulation here, then it will generate a heat current. Now this is the so-called spin Peltier. I will not go into details here anymore. I just point out a recent experiment by the group of Kimura in Kyushu University. Here's the structure. You're driving a charge current through this ferromagnet, which becomes hot and thermally injects a spin current into this copper layer here. And the spin accumulation generated is detected by an analyzer of the same material. So the interesting effect is that here you see the signals for copper, iron, aluminum compared to permalloy copper, and we see it's strongly enhanced. In this case, it turns out that the spin-dependent Seebeck coefficient is much larger than the charge Seebeck coefficient. We can explain this simply by this P prime, which is clearly larger than 1. It means that the upspin electrons are electron-like, the downspin electrons are hole-like for this type of band structure. So the main topic of today is more the spin thermoelectrics with YIG, and this is a quite different topic. As indicated by Professor Saito, this is the basic experiment. So we have again a bilayer of a ferromagnet and normal metal, but the ferromagnet is insulator now. It makes no use to put a voltage over this. There's no current, nothing will happen. But experimentalists showed, and that was that heat, the temperature difference, does inject a spin current. Now this was a huge surprise because 200 years of thermoelectric research completely fails to explain this phenomenon. So the material here is, as we heard, YIG or YIG. Now according to Howard Phillips Lovecraft, YIG is a reptilian monster. But for a scientist, it is a real beauty, right? Here you see the beauty. So this is the crystal structure of yttrium iron garnet. Now, the nature of YIG is controversial. There is a guy who's called Richard Feynman who tries to tell us that YIG is a ferromagnet. Don't believe it. It's a ferrimagnet, right? Here is a cut of the crystal structure. Here we have this network of oxygen ions. Yttrium is just non-magnetic, it doesn't do anything. There are two types of sites, tetrahedral and octahedral sites, which are filled by an iron magnetic moment with the size of 3 divided by 2, or 5 divided by 2, but there's more, they're antiferromagnetically coupled, but there's more of one than the other, so a net magnetization remains. So it's a good insulator, it's a nice Curie temperature, it has several very favorable effects. The most important one now is the high magnetic quality factor of about 10 to the 5. So there are many applications for YIG. It's maybe the most useful magnetic substance at all, from all of them, because of these different properties. I would like to point out that it is being recently used for quantum information transducers by the Nakamura group. There's only one field of application which has not yet scored, and this is jewelry, because YIG is usually black due to impurities. So I guess there is still some property which people could work with. Now, in order to understand the spin-Seebeck effect, we have to understand, I have to introduce another effect, which is the so-called spin transfer total. I try to sketch here what is happening for a sort of a tri-layer spin valve, in which we inject some spin accumulation into the normal metal layer here, and we inject the spin accumulation in the direction here, which points upward. Now let's assume that we have a ferromagnet here which is not collinear to the left one. And let's assume it's just at right angles for simplicity. Now the upspin electron is then not an eigenstate in this ferromagnet, whether it's an insulator or a metal. So it must be reflected. It can be reflected either as an upspin electron, that would be a normal scattering process, but it can also be reflected as a downspin. And if you have a good electric contact here between the normal metal and the ferromagnet, this spin flip process is dominant. Now, if we look at the plane to the left of the interface, we see that the upspin electron comes in and the downspin electron goes out. So each electron actually corresponds or contributes to a spin current, right? It's one upspin goes one direction, downspin the other direction. No charge current, but spin current. On the right side of the interface, there is no spin current, as we said. So that means we have a non-conservation of angular momentum at the interface, and according to classical mechanics, it means that we are generating a torque. This torque acts on another angular momentum, which is the magnetization here. So the torque is added to this magnet here, and if it's large enough, the magnet will move. Now the total magnitude of this torque is, of course, not just one electron, but all the electron contributions have to be summed. Now, if you work this out, you see that the total torque is proportional to a material parameter, the spin mixing conductance, and the spin accumulation. We need a spin accumulation in order to generate a spin transfer torque, because you're coming in with an occupied state in spin up, and we must have an empty state of spin down in which the electron can scatter. Now this parameter here can be formulated in scattering theory of transport, and what we need here are the reflection coefficients for the upspin and the downspin. Now this mixing conductance can be calculated from first principles, and I think we will hear more about it later, but it can also be parameterized or calculated from models. So, if the spin accumulation and spin current which hits this interface is large enough, the magnetization will move. Just like a wind will move the rotor of the windmill, as indicated here. Mechanically, we know that this windmill has a reciprocal, namely the fan. Right? So if we actuate the rotor by some external means, we will generate wind. In spintronics, the same effect exists. If we actuate the magnetization dynamics next to a normal metal contact, we will generate the wind, we will generate the spin current into the normal metal, and this process is called spin pumping. It can be shown that these two are two sides of the same metal. They are Unsager reciprocal in linear response. They are governed by the same parameter, the spin mixing conductance. Initially, it was not obvious that the spin mixing conductance could be large in interfaces with ferromagnetic insulators. And this was first pointed out or cleared up by Professor Gerrit from Beijing Normal University and collaborators, who calculated the spin mixing conductance for yeek and a normal metal, silver in this case. Now this is a rather complicated figure. We do not have to understand everything, but these squares here are calculations of the spin mixing conductance for different interfaces, for different cuts, different orientations and cuts of YIG in contact with the metal. And we see that all these calculations, they give numbers which are of the same order of magnitude as the Scharvin conductance, which is the number that corresponds to the number of channels, transport channels in the normal metal. Now it turns out that if we do the same calculations for ferromagnetic metals, we also find numbers of the same order of this Scharvin conductance. So the conclusion from this plot is that the spin mixing conductance and spin transfer torque effects on magnetic insulators are of the same order of magnitude as those on metals. So they are simply large. And they go roughly proportional with the density of magnetic moments at the interface. Okay, so now we can, I can sort of paraphrase again what has been explained already by Professor Seidel, namely the physics of the spin-Seebeck. Let us first understand this bilayer system at equilibrium, but at thermal equilibrium, so finite temperatures. So if we heat up, if we heat up the total system, we know that we will excite degrees of freedom. These are the phonons, but these are also the elementary excitations of the ferromagnet, the so-called magnets. So at finite temperature, the magnetization will move. Now, the moving magnetization at the interface will generate spin pumping, so a spin current is injected into the normal metal. So this would imply that we do have a spin accumulation here. Now, such a process would correspond, so remember we said we are at thermal equilibrium, would correspond to an energy transfer, spontaneous energy transfer. So the ferromagnet would get colder, the normal metal would get hotter. This is not possible because of thermodynamics, because it violates the second law of thermodynamics. Now, as Professor Saito told us already, what we forgot here is the thermal excitation of the normal metal. In normal metals, we know that we have a phenomenon called Johnson-Nyquist noise. These are random thermal currents excited. It is well known, of course, for the charge degree of freedom. But these random Johnson-Nyquist currents are also randomly spin polarized. And the spin polarized contributions will hit the interface, get absorbed, and generate a random spin transfer torque on the ferromagnet. This corresponds to a net spin current, which, if you calculate things properly, is exactly equal to the spin pumping current. So there is no spin accumulation at thermal equilibrium, and there shouldn't be. So this is fine. Now, if we do the spin-Seebeck experiment, we are selectively heating one side of this bilayer, right? So this one is now fluctuating stronger than before, while the magnet is still cold, so from the other side nothing happens. So that means we will increase the spin current, the spin pumping current with respect to the other. As a consequence, we generate the spin accumulation, we generate the spin current, and this can be detected by the inverse spin Hall. The magnitude is, surprise, surprise, proportional to the temperature difference and the spin mixing conductance. Right. So theoretically, we can calculate the spin-Seebeck effect basically two different ways. One way is in terms of the correlation functions of the spin dynamics of the spin S at the interface. There's a term which is the cross product of the spin and the dynamics here, this S dot. There's another term which is this spin transfer torque term, which can be expressed in terms of a random magnetic field at the interface. Now, both this prefactor alpha prime and this random field H prime are governed by the spin mixing conductance. An alternative way to formulate the same physics and in the given approximations, it gives exactly the same result, is Fermi's golden rule calculation in terms of the interface exchange. In this case, you have two different systems. You have here the normal metal with or without a spin accumulation. We have here a magnon system, a magnon of spin waves. Now this one here is the spin current, the same spin current as here, and it is governed by the density of states of the magnons and the difference of the distribution functions of the magnons on one side and the spin polarized electron hole pairs on the other. So I guess this is all pretty established. Now we can now play the same games as before and write down a Unsager matrix, in this case for a completely collinear system, and we find new matrix elements which correspond to new effects. Now the spin Peltier effect has already been found, but other effects are still not yet observed. I would now like to come to a very interesting experiment which was carried out by Professor Uchida, also at Sendai. What you see here is the temperature dependence of the spin-Seebeck effect. The upper curve here shows the magnetization. If you heat up a ferromagnet, right, the magnetization goes to 0, and according to mean field theory, it should go like the square root, and the experiment nicely agrees with such a square root scaling. The spin-Seebeck effect, however, it turns out to be strongly suppressed at higher temperatures, so it goes like the cube of the temperature. Now this was quite of a disappointment because you would like to use the spin-Seebeck effect for thermoelectric generation of power also at higher temperatures. So it's important to understand what is happening. In order to understand this, we really have to take into account that Gig is a ferrimagnet and not a ferromagnet. Now let us recall what is the ferrimagnet. So we have an order of two different spins, and one is larger than the other. The low energy mode of a ferrimagnet is the magnetic mode, where basically this majority spin is precessing in the right direction. However, the opposite ones, they see not only the applied magnetic field, but also the exchange field. And this exchange field is in the opposite direction to the magnetic field, and the magnitude is much larger. So this one, the optical mode, is usually at a much higher energy than the lower one. And you see here an example, a classical example of magnetite or rust, neutron scattering experiments of the spin wave spectra. You see the ferromagnetic mode, and you can also see the optical ones. Now temperature, room temperature here is about here. So the antiferromagnetic modes, they do not play a role at all. So far so good. But how is this now in Gig? Now Gig is quite complicated. So we would like to use a little bit more involved model to do that. It's still beyond first principles calculations, but the next best thing are atomistic simulations, in which we have classical spins on each atom, right? And each of these spins is governed by the Landau-Lifshitz-Gilbert equation. The effective field is not the applied field, not only the applied field, but also the exchange field of the neighboring ions, right? So we have to solve an equation like that. The effective field looks like that, and we have to take into account, we have a stochastic system, thermal system, we have to take into account a random magnetic field with a correlation function which we take to be simply white and proportional to the damping parameter alpha. So this is a famous fluctuation dissipation theorem for magnetic systems. Now this is a well-defined problem, and you just need a big computer and calculate the time dependence of these spins, and then you can calculate the correlation functions. And if you Fourier transform them, you're getting the power function. So this is the power function, sk omega, and again if you integrate that, you can get the spin-Seebeck. Now this power function now turns out to have singularities, and the singularities correspond to the spin wave excitations. Now here you see the calculations, just numerical calculations, and I plotted here. And on the left side you see the results of a classical spin model, long time ago. On the right side are the calculations, which were carried out by Joe Barker. You see great agreement here between the dispersions coming from the calculations and from the models. Here you see the temperature dependence of these correlation functions. This problem with this, what we are solving here is sort of is a strongly nonlinear system. The LRG equation is nonlinear, and the whole system is nonlinear. So in these calculations, magnon-magnon interaction processes are completely taken into account. Increased magnon-magnon scattering at higher temperature leads to a reduced lifetime of the excitations, broadening of the spectrum. So that's quite obvious, but we see an additional effect. We see here one of the bands which goes down quickly. Now this is actually the antiferromagnetic mode, the optical mode, which moves in the exchange potential of the magnetic modes. Right? And since at higher temperatures we are disordering the system, this exchange potential goes down, and it goes down strongly. Here you see the KT level of occupation of spin waves. And clearly, if you go to higher temperatures, you see that these optical modes get strongly occupied. This, by the way, is the sublattice magnetization as a function of temperature, and it goes to zero at the decent temperature. So the parameterization. Now there are neutron scattering experiments which were carried out already a long time ago. The agreement with the experiment is very nice. Now let's come to the comparison with Uchida's experiment. So this is again the band structure, and we have now indicated that the optical modes in blue, and these are the ones with the chirality which goes opposite to the ferromagnetic mode. So these optical modes, they pump actually a spin current which is the negative of the one from the main mode. Right? And what you see here is this delta, the splitting as a function of temperature. And this is just a 45 degrees line, and we see that around room temperature, these optical modes become occupied. So, at higher temperatures, there will be an additional effect which reduces the spin-Seebeck effect, because spin waves with an optical polarization, with an optical spin pumping, an opposite spin pumping current, contributes and additionally suppresses the spin-Seebeck effect as observed. Okay. Now let's play this game a little bit further, and I would like to draw your attention of a slightly different material, which we call GIG. So it's not GIG, but GIG, in which the yttrium is replaced by the rare earth gadolinium. This is part of a fascinating family of compounds in which the rare earths substitute the yttrium. So, especially interesting here is the right-hand side of the lanthanides. Because these materials, they have the phenomenon of compensation. As a function of temperature, there is a point at which the magnetization here goes to zero. Now these are experiments, and this paper by Gepäck et al. Is a collaboration between experimentalists and theoreticians from many groups, and Sendai is one of them. Now this is the result of one of the groups. I forgot exactly what group it was, but you see that the magnetization indeed goes to zero at a certain temperature. Now what you see here is the spin-Seebeck effect for the same material under the same conditions. And exactly at the compensation temperature, there is a change of sign of the spin-Seebeck. Then, at a low temperature, there is another sign change. And I would like to convince you that we understand perfectly well what is happening. First of all, you see some simulations of, again, Joe Barker of this system. What you see here is the magnetization as a function of temperature of the different magnetic sublattices. So there are two iron sublattices and the gadolinium one. Now it turns out that the magnetization of this gadolinium sublattice goes down much quicker than that of the iron. So the gadolinium sublattice is weakly coupled to the rest and therefore melts much earlier than the others. And that means that at some certain point here, the total magnetization is zero, while the magnetization itself is not zero. Now here you see the picture, how it happens. So this gadolinium melts earlier, and at some point, so the gadolinium is parallel to the minority iron atoms. If you take away the gadolinium, then the majority ions will win, but they point in the opposite direction. So if you apply a magnetic field, the whole magnetization will fit at this point. Now in the Maekawa group, they looked at this problem in a simple two-subnet model. in which, in which the irons are supposed are sort of treated as one single spin band with interaction with the gadolinium. Now, at the compensation point, we know that the whole thing flips, right? And clearly, at such a point, so what is pumping positive just above the compensation point will pump negative at the what pumps positive, say, on the high temperature side, will pump negative on the low temperature side, because the compensation completely flips. So this actually explains quite simply the first sign change. But what's the second sign change? Now the second sign change can again be explained in terms of the balance of the exchange of the optical modes and the ferromagnetic modes. So what you see here are the gadolinium and some of the iron modes, which are strongly hybridized. This again has been investigated a long time ago, and that is well known. But here you see the optical mode with a different color, with a different sign of the spin particle. Now here we see at 3 different temperatures around the second sign change, the spin wave spectra compared with the KT level. At low temperatures, we see that only this lowest band, the ferromagnetic mode, is occupied, and we get the spin-Seebeck effect, the normal sign. If we increase the temperature, we see that increasingly this acoustic mode with the optical and opposite spin polarization is occupied, and at some point it wins. And this explains, in this case, the change of sign of the spin-Seebeck effect at low temperature. Now, the final topic I have for you today is the strong coupling of magnons with phonons. I'll skip the photons today. This is part of spin mechanics, the coupling of the spin degree of freedom and the magnetic degrees of freedom. There has been a workshop on this topic in Munich this summer, and in February 2017 there will be another one in Banff, which is in February when the skiing is best. Right. So magnetoelastic coupling can be understood in terms of the magnetic anisotropy. Right? We know that magnetism is locked to the lattice by spin-orbit interaction. This gives you the magnetic coercivity. Right? So that means also that if you deform the lattice, then the equilibrium magnetization will change. It will. So if you sort of have this shear strain on the lattice, then the equilibrium magnetization will change in order to fit this anisotropy potential. By strongly deforming the lattice, you can even switch the magnetization. Now this is a simple static picture, but of course in general this will also affect dynamics. Now the magnon-phonon interaction, which is caused by this, has different effects. It can sort of generalize thermalization of the lattice and spins. There is an effect which is called the magnon-phonon drift, which affects, magnon-phonon drift. And there's also the magnon polarons, which are the mixed elementary excitations of the magnetic system and the lattice system. Now basically this is just 2 coupled harmonic oscillators, right? The phonons are a harmonic oscillator system and the magnons are. So basically it's a 2-level system, but it is dispersive. In this plot you see the dispersion of the spins and of the magnons and the phonons for parameters of yig. So this is a logarithmic plot, but the phonons have a linear dispersion, right? And the magnons have roughly a parabolic dispersion. Now you have to look very precise to see that these two at the crossing point indeed have an interaction which generates an anti-crossing. Precisely at this anti-crossing, the elementary excitations are not magnons, are not phonons, they are these coupled magnon polar. Now the question is, how can you observe the effects due to this apparently tiny coupling between these systems? And here again, the experimentalists have guided us insofar that light spectroscopy is a nice way to do that. Especially the so-called pump probe experiments. Excite experiments with the material, with the laser, and then you observe the induced magnetization dynamics by another laser making use of the magneto-optic Kerr effect, for example. So this would be a picture. So you have a pump, which is, say, at the origin, and then after the pump, in very short time scales, you're scanning the whole sample and look what the magnetization distribution due to this pump is. Now, there are some fundamental issues still on how the light exactly generates magnetization dynamics. It can be done non-dissipatively in terms of the so-called inverse Faraday effect, or it can simply, by the fact that the laser heats the sample just on the laser screen. Because the laser sort of will expand the lattice, it will generate phonons, and these phonons again interact with the magnons and generate spin dynamics. The basic problem is quite easy. Again, it's just a 2x2 equation, but it's sort of for the whole, you have to do this for the whole case space, so there is some calculation to be done. Calculations or the interpretation becomes easy if in the beginning we assume that the excitation is by a line source and the detection is also on the line, because that reduces the problem to one dimension. Now here you see the result of the calculations. At first we are switching off the magneto-elastic interaction. In that case, we see that within these time scales here, nothing happens. The excitation is localized. Reason for that is the extremely small group velocity of magnons. Magnons really do not like to move fast. They are very slow. Situation changes completely if you switch on the magneto-elastic coupling. Here you see now, again for Jäger parameters, what happens in the same situation if the phonons are included for small and for larger broadly. If you look at these here, we see clearly that we have wave packets which are going away from the excitation, and the velocity of this wave packet is exactly the sound velocity. What we see here is, in fact, the strongly coupled magnon polarons, which move with the velocity of the sound, but they carry the magnetizations with them. Right. These are now two-dimensional results for a point source excitation, or for a localized excitation. And we see nice pictures with a certain symmetry. This one is assuming that excitation is done by the Faraday effect. These are the spectra which we would expect if, by the laser, we exciting pressure waves in the magnetic field. And this is how it looks if we have shear waves excited. We see that the radius is different here in these two cases. The reason is that shear waves, they excite the transverse polarons, which have simply a much slower sound velocity. Now we can compare this with experiments. You see the theory on top, and the experiments by the Riken group, Ogawa and collaborators below. And we clearly see the difference. First of all, we see two ringings, the theory and the experiment, which have exactly the same symmetry. So these are the pressure waves, and these are the transverse waves which are excited by shear strain. In these experiments, we do not see any inverse Faraday effect excitation. We can also look at the magnetic field dependence of these patterns, and we see in general, in theory and experiment, a weakening of the signal as well as an increase of the frequency, which can be explained simply by the shift of the spin wave gap by the magnetic field. Okay, so let's come to the conclusions. So I think I'm nicely in time, right? The thermoelectrics with respect to spin caloritronics has two effects. There is the spin-dependent effect, which exists only in metals, and there is a collective effect, the spin-Seebeck or spin-Peltier effect, which can be seen, observed in insulators. We have to be careful. Ferrimagnets and ferromagnets are, as far as thermal effects are concerned, also very different. So a simple ferromagnet does not work to describe YIG at room temperature. We have seen that the spin-Seebeck effect, which is now basically well understood, can be used as an instrument. We do not look at the spin-Seebeck effect itself. We use it as an instrument to understand spin correlations in complicated ferromagnets. The example which worked very nicely was for gadolinium iron garnets, but there are also experiments on, say, multiferroics, which see interesting features which are not yet well understood. But sort of, you're now changing from Seebeck effect as an effect itself, but as a new instrument to measure things we cannot measure by neutron scattering, for example. I also try to convince you that photons are important as well in many spin transport phenomena, and I think we have to do more research in that direction. So, for those maybe who are interested in this type of work, there is a postdoc position available at Sendai. I would like to thank my collaborators, which of course includes Professor Seidler and collaborators. Thank you very much for your attention.
Thank you. Any questions, comments? Maybe I have a question. So in your